So as a reminder, the formula to find the z-score is that the z-score is equal to whatever data value you're looking at. Remember that data values and z-scores correspond to one another. It's almost like a, XY coordinate pairing when we're looking at our graphs. Every specific X value, data value has its own z-score, and every specific z-score has its own data value. They are linked together with these formulas. So if I'm asked to find the z-score for a certain data value, this is the data value I would plug in, this X value. All right, and we want to know, remember the z-score is how many standard deviations away from the mean, which is why we subtract the mean, the distance between the data value and the mean, but we want to scale that to be standard deviations, which is why we are dividing by sigma. We're dividing by the standard deviation. Now, this is a formula that you are allowed to write on your formula sheet. Okay, so if you struggle with memorization, this is one formula I encourage you to go ahead and put on that formula sheet you're allowed on that exam. All right, again, this is where Z is the z-score. X is the specific data value that we are looking for the corresponding z-score of. Mu is the mean, and sigma is the standard deviation. So let's look at an example where maybe we're not asked, like the last example, for an exact value that was nice, where we could just draw a number line out and see what the corresponding z-score was. Suppose that X is normally distributed, is a normally distributed random variable with a mean of 5 and a standard deviation of 6. Write the distribution notation for this situation. All right, when I ask for this, I am looking for you to say that X is distributed how? X is normally distributed with a mean of 5. Remember, mean goes first, and standard deviation of 6. Standard deviation goes second. You will be tested on this, okay? You need to be practicing this. Whether the homework asks you to write this out or not, you should be practicing writing your distributions as you go. You should be doing this for normal. You should be doing this for uniform. Even though I didn't specify it in binomial, try to do it in binomial, okay? N and P were the two key values in those as well. All right? So this is the distribution we're looking at. That gives us our mu. That gives us our sigma, right? That's our mean and our standard deviation. Suppose X is 17. That's the data value we're looking at. Write this, or what is the z-score that corresponds to this value? So if I want to find the z-score, it's the same thing as X minus the mean divided by sigma. So we're taking the difference between our data value, that was 17, minus the mean, that was 5, right? From our situation, divided by 6. That's our standard deviation. Now, if you're putting this into your scientific calculator right now, you have to be careful that you either wrap the numerator in parentheses, or you do a two-step process where you subtract 17 minus 5 first and then divide by 6, because this is a grouping symbol, and parentheses or any other grouping symbols go first in our order of operations. So this is 12 over 6. This is a positive 2. This is one where our z-score was a nice whole number. If I wanted to, I could have found this example by listing out my situation in 5 in the middle, 1, 2, 3 above, 1, 2, 3 below, and I'm adding a standard deviation of 6 in between each of these values. 5 plus 6 is 11. 11 plus 6 is 17. 17 plus 6 is 23. All right, these are my data values, my X values. If I was looking at z-scores, the mean is always a z-score of 0. This is 1 standard deviation above. This is 2 standard deviation above. This is 3 standard deviations above. Just to show it again, I would be subtracting standard deviations to find the values on the other side. So that's 5 minus 6 is -1. -1 minus 6 is -7. -7 minus 6 is -13. The z-score of -1, the z-score of -2, a z-score of -3. So we can see that's data value of 17 lined up with a z-score of +2. That worked out for us right there. But again, you can see it with the formula version. Let's try it again. Okay, I encourage you pause it, see if you can find for x equals 1. X equals +1 is not a nice value. Okay, I can see though that, hey, whatever my z-score is, it should be something between 0 and -1, because +1 as a data value is somewhere between 5 and -1. All right, so I can kind of estimate, but I don't know the exact value until I use my z-score formula. Z-score is equal to the data value 1 minus the mean, which was 5, divided by 6. Okay, I know I didn't write the formula again, but it's right there. Data value 1 minus the mean, which was 5, divided by the standard deviation, which was 6. Again, you want to simplify your subtraction first because it's grouped together with the big parentheses. So we have -4/6. -4/6 is -0.66667. Depending on what you're asked to round to, I'll do 4 decimals. All right, but I think in my filled in notes, I put -0.67. All right, it's 2/3. It's those repeating sixes. But again, visually, we could have guessed approximately where it was somewhere between 0 and -1. And we can see that -2/3 or -0.67 is indeed between 0 and 1. But this gives us the accurate z-score. Round it a little more. Usually when we do z-scores, we don't have that many decimal values. Something rounded to 2 is, just fine. I didn't write it before, but let's actually talk or describe what this is again. Okay, just to remind you what a z-score is. This means that the data value of 17 is 2 standard deviations above the mean because it was a +2 z-score. All right, -0.67 z-score means that the data value of x equals 1 is 0.67 or 2/3. Okay, it's not even a whole standard deviation below the mean. Notice that I didn't write it's -0.67 below the mean. All right, the word below indicates that negative value. And I could have said for this, I could have said to the right or above. For this, I could have said to the left or below, because you can see where the mean is our z-score of 0. We have above or to the right. We have below or to the left. Those words are kind of interchangeable.